Alright everybody, welcome to this edition of Video Notes, our first of the year for AP Chemistry. That's right folks, these notes are for AP Chem. And they will be due on Tuesday the 11th. Okay, so getting a jump on things this year, we're going to be talking about just a quick review of the atomic model. So how did we get to where we are in our understanding of what an atom looks like? So here we go. Alright folks, so first guy that we need to talk about is this guy, Democritus. Okay, he gets credit for coming up with the idea. So he was a Greek philosopher who lived well over 2,000 years ago. Okay, and he just basically had the statement that matter is made up of tiny indivisible particles called atoms. Now, there was no proof of Democritus' claim at all. He was just a philosopher, he was not a scientist. And in fact, there wasn't any proof of his claim until more than 2,000 years later. Along came this guy here, Antoine Lavoisier. Okay, he came up with the law of conservation of mass, right? Matter cannot be created nor destroyed. So this is kind of our first start to prove of Democritus's idea. Oh, you can't destroy matter, right? And then along came this guy right here, Joseph Proust, okay, who had the law of definite proportions, and he basically said, hey, if you take water from two different samples, two different places, it's the same. It's the same amount of oxygen and the same amount of hydrogen exactly every time. Okay, so now we've got these ideas that, man, there are maybe these particles that we can't see that make up matter. But the definitive proof was still out there. By the way, just so you know, you won't have to spit back to me these names here. I'm just kind of giving you an overall view of what the discoveries were leading up to this. Okay, now here's where we start getting some definitive proof of atoms. Along came a guy named John Dalton, and he ran some experiments with different compounds, and he found that you always had the same proportions that went into those compounds. One of the easiest to explain is this, is CO2. And he always found this, that when you made carbon dioxide, which they knew had certain properties, you always had 1 part of carbon and 2 parts of oxygen. And so that begins to say, well, hey, there must be proportions or particles that come together in order to make these compounds. And so based on the evidence that he collected, Dalton made 4 postulates, or 4 kind of assumptions about what's going on with these small particles. Okay, he stole from Democritus, and he called these tiny particles atoms. All right. He said all atoms of every element are identical to one another. Okay, you can't create or destroy them, like Lavoisier had already said, right? But they can be recombined in many, many different ways. Okay, and then when compounds are formed with atoms of different elements, right? A given compound always has the same relative numbers and types of atoms, right? So carbon dioxide is always carbon dioxide. Water is always water. Okay. Now, while Dalton's discovery was revolutionary, okay, and leads us toward really understanding that there are atoms, he wasn't totally correct. So here's my question to you, which we'll discuss on Tuesday. Which of these postulates were proved to be true and which were not? Okay, so let's fast forward a few hundred years to J.J. Thomson. Okay, at this time we had really accepted the idea that atoms were present, but we didn't really know what they were made up of. Okay, we didn't know that they had negative and positive charges and all that stuff. So they had these things called cathode ray tubes, where you hooked it up to a battery, and this stream of something, in fact it ended up being particles, went through the tube. Okay, they didn't really know what this stream of particles was made of. So along came J.J. Thomson, and he decided, well, let's take this stream of particles and expose it to an electric field, right? So you can see right here, here's his electric field, a positive and a negative charge on each side. Okay, and what he found is this: when he did that, the stream bent. And if you notice, it is repelled by the negative charge and attracted by the positive. That means, what charge is it? oh, it must be negatively charged, right? He also found this, that the amount of deflection or bend in the beam depended on the strength of the electrical field, which means that this must be made up of particles, because if you expose it to a stronger field, it bends more because you've got more force accelerating the particles as opposed to a weaker field which would bend it less. So the inference from this experiment is this: since you can't create particles out of nowhere, they must be coming from atoms, and therefore atoms have electrons, which are negatively charged, right? So that's kind of the inference. And then a further inference is this, right? If you have electrons that are negatively charged and atoms are neutral, there must be what? There must be positive charges, right? So this was groundbreaking because it led us to understand that atoms aren't just solid balls. They are made of positively and negatively charged particles. All right. Here's one of my favorite experiments and one of the most famous experiments of all time, right? This guy named Ernest Rutherford gets credit for it, okay? And he had some radioactive, he did this. He wanted to find out, are atoms really solid balls, right? Are they really solid? So he had this lead block with radioactive material in it, right? And that radioactive material could shoot out particles, okay? There were alpha particles, which have mass. Those alpha particles would shoot out. And he shot them at some gold foil right here. That is gold foil. It's really thin, only a few atoms thick. And he figured this: if he shot these particles, which are solid, at the gold foil, and atoms are solid, they should bounce off. What he found though was something the opposite. He found that atoms are actually not solid, and that most of the particles pass straight through the gold foil, right? Most particles pass straight through. And some had a slight deflection like this. But he wanted to know this: there can't be nothing there if this is something, right? So he kept at it. He kept at his experiment. And what he found finally he found something that bounced back. It was actually 1 out of every 8,000 particles bounced back. Okay? Crazy. So, what is the inference from this experiment? Well, okay, what this allows us to infer is this, right? That atoms are made up of a very small and positively charged nucleus, right? That's because, A, that nucleus is really hard to hit. And he knew it was positively charged because of the few alpha particles that slightly deflected, that didn't go straight through the gold foil. That means they got close enough to the positively charged nucleus that as they went by, they were repelled by it and sent off at an angle. Okay. Then he concluded this: if the nucleus is positively charged, the electrons must be occupying the space around them, and those electrons are very small in their mass and size. Well, thanks for tuning in, you guys. That's just a short history, a few things of background that hopefully you kind of sort of remember from Gen Chem, but are important for us to remember as we start studying the atom in detail. Thanks for tuning in. We'll see you in class on Tuesday.